Hello and welcome to the second video on the topic of moments. So this time we're going to have a look at equilibrium, whether forces and moments together are balanced. So it will make more sense when we do some questions. So I'm not going to talk too much. I'm going to try and get forward to when we actually try and have a look at some questions and work through the solutions. So on that note, let's get warmed up with 4 warm-up questions. So have a go at these, press pause now and try them on your own, and when you're ready to see how they go, how they work out with their solutions, press play and I'll guide you through them. So okay, let's have a look now at question 1's solution. So this one here is just about drawing a diagram to illustrate information given. This is a crucial skill for A-level. You'll be given lots of information sometimes and just asked to work out what it all means. So have a mass m kilograms fixed at the end of a light horizontal rod at a point P. So we're told about this light horizontal rod, so let's just draw this out. So light horizontal rod, so let's just draw it like this. So this mass is at the end of a rod at point P. So what I'm going to suggest we do is we draw on point P at the end of a rod here. That's at the end, so let's call that point P. So the rod is pivoted at the point O, k meters from P. So what I'm going to suggest we do now is add in this bit of information, pivoted at O, so O will probably be somewhere about halfway along. I'm going to say that's O. And also, we're told that it's k meters from P. So again, let's add this in, k meters away from P. So we can add in a straight line just to illustrate that it's that distance from P. Okay, so that's k. We're also told that a second mass of 0.5 m is fixed 1 meter from P, and also this is between 0 and P. So let's add in the second mass, which I'll just put here. Now we're told that's 1 meter away from P, so I'll just add in that it's 1 meter away with a illustration that that's 1 meter. So we're almost done. What I've not done here is added in the masses. So the mass which is at the end at P has a mass of m kilograms. So I'll just draw this in here. So it's got a mass of m. If its mass is m, its weight will be mg. And finally, the one which is here has a mass of 0.5 m. So that will have a weight of 0.5 mg. So I'll just add this in as well as 0.5 mg. So that's part 1 done. We've drawn the diagram. The next thing to do now is to answer some questions relating to this diagram. So let's move on to question 2. Question 2 says, given that the resultant moment about O is 7 mg, find the value of k. So this relates to question 1 where we drew the diagram. So let's just remind ourselves of what we drew from before. So that's what we had. And so now let's just fill in the details and work out what this value k is. So relative to O, if we take moments about O, we should be able to work out what we need. So relative to O, all the moments are clockwise. There's 2 forces, 2 weights, 0.5 mg, and also mg as well. So all moments are going to be clockwise. So let's start with P. So P is k meters away, and P is a weight, a force of mg. So P is going to be mg, the magnitude is mg, multiplied by k. So that's mg multiplied by k, whereas adding on as well, we've got this one 0.5 mg. So 0.5 mg is the magnitude of the force, the size of the weight. However, we need to multiply this not by k, because this one's a bit closer to O. This one here is 1 meters in, so the distance from O is k minus 1. So that's the resultant moment about O, and we're told the resultant moment is 7 mg. So we form the equation like so. We can now cancel common denominators. If we look carefully, in fact not even that carefully, we can see that mg is a common factor for each of these terms. So we can cancel an m from each, and as well we can cancel a g. So that simplifies it quite a lot, in fact. So now we have k plus 0.5 times k, so that's 0.5k, 0.5 times minus 1, so that's going to be minus 0.5, that equals 7. So if we simplify this, k plus 0.5k, that's 1.5k. Then if we add 0.5 to both sides, we get 7.5. Finally, if we divide both sides by 1.5, k will be 7.5 divided by 1.5, which is 5 meters. So k must be 5 meters, and we're done. Question 3. We have two forces acting on a particle P, as shown in this diagram below. Calculate the resultant force acting on P in the horizontal direction. So here this force is acting at an angle. What we need to do now is to resolve this force. So if we resolve this 12 Newton force in a direction along P and perpendicular to it, we'll get this. Remember, the force going along resolved is always the hypotenuse cos the angle, so 12 cos 60 along, and the force going up will be 12 sine the angle, so 12 sine 60, like so. So just thinking of horizontal forces, then the overall force in the horizontal direction will be the 12 cos 60, whatever that happens to be, minus a force opposing it, so minus 6. So let's calculate this now. So 12 cos 60 minus 6 is 0. So there's a 0 Newton force in the horizontal direction. That means this particle is not accelerating in the horizontal direction. It will therefore only be moving exactly vertically upwards. So net force here is 0. Finally, question 4, we have a different diagram, and we're told to use the information in the diagram to calculate the resultant moment about P. So this force down here, the 8 Newton force, the line of action of this is already given perpendicular from P, so that's very easy to calculate. This one though here, the 12 Newton force, is acting at an angle. So we need to calculate the direct distance of the line of action of this 12 Newton force from P, so we need to calculate a perpendicular distance along sort of this line. So what we could do is extend this 12 Newton force's line of action to calculate and see what we need to work out in terms of distance from P. Something like this. So yes, what we need to calculate is the distance of this red line. So as we can see here, we have a right angled triangle. This is a right angle. The hypotenuse is 0.4, and we need to work out the size of this side opposite to the 30-degree angle. If we need to calculate the size of a side opposite to an angle, that's going to be the size of the hypotenuse, 0.4, multiplied by sine of the known angle, so 0.4 sine 30. So next, what we can do is work out the size of the moment from this 12 Newton force. Now this is acting in a clockwise direction. So for the 12 Newton force, the moment from this one is the magnitude of the force, so 12, multiplied by the distance of the line of action from P, which is 0.4 sine 30. So if we calculate this next, 12 multiplied by 0.4 sine 30 gives us 2.4 Newton meters in a clockwise direction. Whereas this 8 Newton force will be acting in a anti-clockwise direction. So the moment from the 8 Newton force will be 8 multiplied by its distance from P, which we've already been given as 0.3. 8 multiplied by 0.3 gives us 2.4, that's Newton meters, anti-clockwise. So we have 2.4 Newton meters going clockwise and 2.4 Newton meters going anti-clockwise. Therefore, the resultant moment, because you have equal and opposite magnitude moments, the net moment is 0. 2.4 clockwise and 2.4 anti-clockwise will exactly cancel each other out. So question 3, we had a resultant force going horizontally of 0. In question warm-up 4, we've got a resultant moment of 0. So what is this all about? Well, let's have a think about it. This is a case of equilibrium. So what does equilibrium mean? It means that when a rigid body is in equilibrium, the resultant force in any direction is 0, and also the resultant moment about any point is 0 Newton meters too. So 0 resultant force and 0 moment. We can simplify many problems involving rigid bodies by choosing which point to take moments about. When you take moments at a given point, you can ignore the rotational effect of any of these forces acting at or through that point. So let's now have a look at an example which is fairly intuitive, an example for intuition. So this diagram here shows forces acting on a light rod APB. Given that AP is 6 meters and the resultant moment about P is 34 Newton meters in the clockwise direction, find the distance from P to B. So let's consider this one carefully together and see if we can get it correct. Clearly, around point P, there are two different forces acting. One will be clockwise, this 32 Newton force, one will be anti-clockwise, this 5 Newton force. So let's consider it in terms of clockwise and anti-clockwise. So the clockwise force will obviously be this 30 Newton force. So that's going to be 32 multiplied by PB. Whereas the clockwise force, the anti-clockwise force I mean to say, will be clearly based off this 5 Newton's force. So this one we know more information about. We know the magnitude of the force, which is 5, and we know the distance this time. We know it's 6. So 5 times 6 equals 30 Newton meters. So if we put these two together and realise that the resultant force is 32 Newton meters, so 34 Newton meters in the clockwise direction, we can work out therefore PB. So the resultant moment, the prevailing moment, is going to be clockwise. So this one here, the clockwise moment, is going to be greater than the anti-clockwise, this one. So therefore, if we do 32 lots of PB and subtract away the anti-clockwise moment, which is 30, we should have 34 Newton meters, still overall in the clockwise direction. So now, if we add 30 to both sides, 34 plus 30 is 64. So therefore this distance PB is 64 divided by 32. Therefore PB has to be just 2 meters. This is like a seesaw being balanced, okay? So, or some beam anyway. So 5 Newton force, very far away. If somebody's here which is much heavier, it will require only a shorter distance to keep it balanced. Let's have a look at some formal worked examples now based on this idea of equilibrium and moments. So here we've got a uniform rod in equilibrium. A uniform rod means that its weight is evenly distributed. It means that the weight is even throughout. It's not weighted at one end or weighted in the middle. The weight is completely evenly spread out throughout its length. So we have a diagram here, and it shows a uniform rod from A to B with a length 3 meters, and it's got a weight itself of 20 newtons, and it rests horizontally on 2 supports at A and C, where A to C is 2 meters. Calculate the magnitude of the reaction at each of these supports. So the first thing to mention here is what we mean by a reaction force. A reaction force is just literally the reaction to a force pushing down or in the opposite direction. So here, for example, at A, the actual rod will be weighted down at A, so there'll be a reaction counteracting it going upwards at A, and I'm going to call this very simply just RA. So that's going to be the reaction at A. In exactly the same way, I'm going to do the same at C and call that RC. Now, if we remember from before, if something's in equilibrium, which it is, then what we need to realise is the sum of forces in any direction is 0, as is the moments, either clockwise or anti-clockwise. The overall moment, the resultant moment, will be 0 based off any given point. So if we just now consider this point A, so moments about A, in fact I'll just rewrite that, moments about A. And these questions, there are often a few ways of doing them, so just because I'm doing it one way isn't to say my way is the only way. If only your attention span was longer, I could do a 5-hour video, although I'm sure that wouldn't be too interesting at all. So moments about A. So we've got some clockwise moments to consider, and as well some anti-clockwise. We need to fully label this diagram, however. So we've got that a rod has a weight of 20 newtons. It's a uniform rod, so its centre of mass will be at the middle of it. So if it's 3 meters long, its weight will be acting halfway along, which will be 1.5 meters. So it's 20 newtons going down, and the distance, because it's uniform, is half its length, so that's 1.5 meters. So we can add this in to help us solve the question. So again, considering moments about A, what we can say here is clearly that the clockwise moments are just going to be the weight of this rod, so 20 multiplied by 1.5, that's the clockwise moment. Because in equilibrium, this will equal the anti-clockwise moment. So this is going to equal the anti-clockwise, which is from C. We can see from the diagram that from A to C, it's been given as 2 meters. So therefore we know that the distance from A to C is 2 meters. So therefore the moment anti-clockwise from this reaction at C will be the size of reaction of C, which is RC, multiplied by its distance away from A, which is labelled clearly as 2 meters. So now we can simplify and solve. 20 times 1.5 is 30, RC times 2 is 2 lots of RC. Therefore, if we divide both sides by 2, we can see that the reaction at C has to be 15 newtons. We could, if we wanted, do similar to work out the reaction at A. However, it's much easier to think about forces. Because this system is in equilibrium, so because the system is in equilibrium, we can say that the sum of forces in any direction is 0. So because our forces are either up or down, the reactions and the weights, we can say that the sum of the forces going vertically is 0. In other words, the reactions acting up will be equal and opposite to the forces going down. The only force acting downwards is the weight of this rod, which is 20. We've just worked out the reaction at C as 15, so we can sub in 15. Ra plus 15 equals 20. Therefore, the reaction at A is going to be 20 minus 15, which is 5 newtons. If you really wanted, you could have taken moments about C, and it would have dropped out that reaction A would have been 5 newtons. There's more than one way of doing these questions, but sometimes the simplest way is to consider forces going in one direction or the other. So we've worked out the magnitude of reaction at each of these supports. So one reaction is 15 newtons at C, and reaction at A is 5 newtons. So if you want to colour code it, we can. There we go. We've done the question. We can now move on to worked example number 2. This one here, we've got a person standing on a rod. So it's a uniform beam, AB, of mass 40 kilograms and length 5 meters. It's resting horizontally on 2 supports, C and D, where AC is the same as DB, which is 1 meter. When a man of mass 80 kilograms stands on the beam at E, the magnitude of a reaction at D is twice the magnitude of the reaction at C. So we can fill this information in now because it's a bit too much to just absorb from this massive paragraph. So this man is standing here. He's got a weight of 80 kilograms. Therefore, if his weight is 80 kilograms, we know that the force due to his weight, the force due to his mass, for gravity, force due to gravity is weight, is going to be 80 multiplied by g. So 80g is acting downwards. Now hopefully we can see from this diagram, he stood, as we look at it, to the right hand side of the centre of mass of this uniform beam AB. This beam is going to have a middle about here. It's got a mass of 40 kilograms. If its mass is 40, that means its weight acting downwards is 40g. Going back to what I was saying earlier, we're told here when he stands on this beam, the magnitude of the reaction at D is double the magnitude of the reaction at C. So at C, if I call the reaction at C just simply RC, reaction at C, then we've been told that reaction at D is double that. So if I call that RC, then RD is going to be double what that is. So rather than calling it RD, I'm going to call this 2 lots of RC. Double RC. So now we can start to consider the distance from A to E. So now what we need to do is just carefully label in some extra information. So we need the distance from A to E. So from A to E is this distance here. As well as that, we know that the distance from A to the centre of mass is going to be 2.5. So we can slowly and surely add on all this information. So let's start doing so now. Sometimes these diagrams can get fairly crowded. There's lots of information to add on, but that's okay. So from A to the centre of mass, it's going to be halfway along the length of the rod, so that's going to be 2.5 metres. A to E is what we need to work out, so from A to E, I'm going to call this just distance x. And, of course, we can add on other distances as we see fit. So the suggestion is, in my opinion, is to consider forces vertically. Because this rod is in equilibrium, then the total of all forces going up or down is 0. So the forces acting up are these reaction forces. So the reaction at C plus 2 lots of the reaction at C must equal the total of the forces acting down. The forces going downwards are the weight of the beam, which is 40g, plus the weight of this man. He's got a mass of 80 kilograms, therefore his weight is 80g. We can now simplify this quite easily and solve it. So 3 lots of reaction at C, 1r plus 2r is 3r's. 40g plus 80g is 120g. If we divide both sides of this equation by 3, we can now see that the reaction at C has to be 40g. So because we know this now, we can add this in. Because reaction at C is 40g, let's just include this. So that's now 40g, and 2 lots of 40g we can now say is 80g. So this will only help us to solve this problem. So what do we need to find? We need to find this distance from A to E. So from A to E is what we need to find. What I'm going to suggest we do is perhaps we can take moments about A, this point A. So because it's in equilibrium, the clockwise moments will equal the anti-clockwise moments. So let's just carefully consider the forces acting relative to A and their directions. So we have here a force here which is 40g, that's 1 meters away. This 40g weight of a rod is 2.5 meters away. The weight of this bloke, he's x meters away, that's what we're trying to find. And also there's a reaction here from D. So let's just add in this reaction from D, because we're going to work out what this is. So this beam is 5 meters long, so from A to B is 5, but D is 1 meter away from the end, therefore from A to D has to be 4 meters. So there's a few forces to work out, but it's all fair enough. So relative to point A, which of these forces are going clockwise? Which of these forces are essentially going down? So going downwards, if you like, relative to A, are this 40g force, which is 2.5 meters away, and the 80g force, which is x meters away. So going clockwise, going downwards, 40g multiplied by 2.5, and also 80g multiplied by x, so 80gx. That's going to equal the sum of the anti-clockwise moments, which are these reaction forces. So this reaction force is 40g multiplied by 1, which is just 40g. And this one, which is 80g, and that's 4 meters away. So 80g multiplied by 4. Now, if we look here, there's a common factor in each of these terms over g. So we can cancel off a g, just divide through the whole thing by g. That makes it much simpler. So this bit here, 40 times 2.5 is 100. 80 times x is 80x. And on this side, we just have 40. And 80 multiplied by 4 is 320. So, if we subtract 100 from both sides, 80x, 40 plus 320, that's 360, minus 100 is 260. So therefore x is going to be 260 divided by 80, which is the same as 26 divided by 8, and that's going to be 3 1/4. In other words, 3.25 meters. And that's number 2 done. Finally, worked example number 3. Worked example 3, we have a uniform rod PQ, which is hinged at the point P, and it's held in equilibrium at an angle of 50 degrees to the horizontal by a force magnitude F, acting perpendicular to the rod at Q. Given that the rod has a length of 3 meters and a mass of 8 kilograms, find the value of F. So because it's in equilibrium, we can therefore conclude that the clockwise moments are equal and opposite to the anti-clockwise moments. So, going clockwise, relative to P, acting down, we can see this 8g force. So this 8g force is going down, so we can label in, because it's going down, the distance, the perpendicular distance of the line of action of this force from P, we can work out fairly straightforwardly using trigonometry. So we need to work out this distance here I've put in green. Okay, that's 8g. The distance from this line of action to P, the perpendicular distance, is this green line. Now, normally before we've been using sine of the angle. Opposite is this 8g force, but we need to go along, so we're after cos 50. We need to work out, though, the hypotenuse, this red line. So how long is the length from P to Q? Well, it says here that from P to Q is 3 meters. Therefore, because it's a uniform rod, and this is therefore going to be its centre of mass, the middle of it, if P to Q is 3, this here is just 1.5 meters. So this distance at the bottom, looks a bit ugly, I'll just get rid of that. Because it's going along and not the opposite, rather than being 1.5 sine, it's 1.5 cos 50. So the moment due to this 8g force is 8g multiplied by 1.5 cos 50. Whereas the force going anticlockwise is F, and the distance from F to P, the perpendicular distance, is the length of the entire rod. The length of P to Q is 3 meters. It's F multiplied by 3. So let's work out what 8g times 1.5 times cos 50 actually is. So we've got 8 multiplied by g, which is 9.8 in any A-level mechanics class, multiplied by 1.5 0.5 cos 50. That gives about 75.792. So 75.792, if I've got that correct. No, I've not. Sorry, 592, not 792, my bad. .592, if I just check that again. Yep. That equals 3f. Therefore, f is going to be 75.592 divided by 3, which is about 25.2 newtons to 3 significant figures. So 25.2 newtons to 3 SF. That's enough worked examples from me. Now it's time for you to have a go. So if you could move on to your textbooks and try page 78 to 80, exercise 4C, have a go at all the questions there if you can. That's what I'd recommend. Check the solutions or ask me if you're unsure. And again, I must say thank you for listening, and do feel free to subscribe. And if you get stuck, do, as I say, find the solutions or let me know in class or give me an email. Or even if you're stuck, leave some comments in the comments section. So take care, and I'll see you all soon, I should hope. Bye for now.